Right, let's see if we can whiz through some energetics then, before we head off to lunch. So we did cover some of this yesterday. I'm going to have a drink, otherwise my voice is going to disappear. We did cover some of this yesterday. We're going to be building on that today, but I won't go back over content from yesterday. So if you're an year 13 student who's just joining us for today, then hopefully you're confident with your year 12 knowledge on this topic, but we will, I won't repeat anything unless it comes up clearly in this presentation. Just got to make sure I keep drinking tea. Otherwise I'm going to lose my voice. Right. So we're going to look today at ionic solids, Born-Haber cycles, polarization, which is not applicable for everybody, but we'll cover that when we come to it, and enthalpies of solution, something that students find particularly difficult, understandably. So if you are an EdXL student or an AQA student, these are the spec points we're going to be covering. I do recommend, as I've said before, that you have your specification on a tab or printed out physically in front of you or whatever, so that you can keep referring back to it if you need. We've also put in some of the major spec points into the, what's it called, PowerPoint as well, so that you can flick back to them if you need. If you're OCR, it's these spec points as well. So, ionic solids. What is an ionic solid? Ionic solids contain a metal and a non-metal, or metal atoms and non-metal atoms, ions, not even, ions, metal ions and non-metal ions held together by the electrostatic attraction between oppositely charged ions. Ionic solids can exist as giant ionic lattices, so that's what they are usually at room temperature under standard states and pressures, standard conditions even. We did do this yesterday, so I won't spend too long on it, but you do need to know your definitions. Standard lattice enthalpy of formation is the enthalpy change when 1 mole of an ionic lattice is formed from its gaseous ions. Sorry, let me clarify. Bad chemist. We did enthalpy change of formation yesterday. What I wanted to say was this is different and we need to be sure that it's different. See, this is how easy it is to get confused. There is a difference and it's key that we know the difference. This is standard lattice enthalpy of formation. Yesterday, we looked at enthalpy of formation. So not lattice enthalpy of formation, enthalpy of formation. Or enthalpy change of formation, you could say as well. This is lattice enthalpy of formation. So the definition is slightly different and you do need to know your definitions off by heart, back to front, inside out. The standard lattice enthalpy of formation is the enthalpy change when 1 mole, so enthalpy is always per mole. So there's got to be some sort of molar constituent to your definition, whether it's 1 mole or if it's relating to the production of 1 mole of something or the use of 1 mole of something or the molarity according to the balanced equation. There's always got to be some reference to molarity. So the 1 mole of an ionic lattice is formed from its gaseous ions under standard conditions. It's under standard conditions because it's a standard lattice enthalpy of formation, but we have to be using, or has to be, we have to make sure that we've included gaseous ions. So not elements in their standard states, but gaseous ions. For example, oh, sorry, my pen's decided not to work. Let's just do that. For example, you might be asked to write an equation which represents this process. This is when states are important because it has to be gaseous ions formed from gaseous ions. And if we're forming an ionic lattice, we're going to be forming an ionic solid. So again, states are important. So we must include them in this case. So for example, I'm starting with my gaseous ions. Ooh, sorry. It tried to do something then. Don't. There we go. So for example, sodium ion and chloride ions form sodium chloride solid. That is an equation which represents the standard lattice enthalpy of formation of sodium chloride. State symbols here are important because they are specific to this process, so you do need to make sure you include them. As new bonds are formed, enthalpy of formation, we're forming ionic bonds. energy is going to be released. When you make a bond, energy is released. So lattice enthalpy of formation is an exothermic reaction. It has a negative enthalpy change. So delta H lattice enthalpy change of, lattice enthalpy change of formation is always negative. To be honest, you don't have to remember specifically that lattice enthalpy of formation is always negative, because you know it's making a bond, and you know that making bonds is exothermic, so it's negative. Just one less thing to memorize then. Lattice enthalpy of formation is dependent on, or lattice enthalpy is dependent on the strength of the ionic bonds formed, and therefore the size and charge of the ions involved. Lattice enthalpy will be larger when what? What are the things that can influence lattice enthalpy, do we think? There's two main things that we'll talk about. Larger charge density, when you've got a larger charge density and a smaller ionic radius, the ions can sit closer together. So lattice enthalpy will be larger when you have smaller ions. Then the more highly charged the ion is, the stronger the ionic bond is going to be, because the greater the attraction will be between the positive and negatively charged ions. And so more energy is going to be released on formation. Therefore, enthalpy change of formation will be larger when you have got more highly charged ions. Okay, those are two things that influence lattice enthalpy of formation. I just like doing these little diagrams just because it's easier to see. So if you've got two ions that are similar in size, they can sit closer together. If you've got ions that are bigger, or even one ion which is bigger than the other one, they have to sit further apart from one another, and that means the bond is going to be weaker. The more highly charged the ions as well. So if we're looking for example, sodium versus magnesium. So sodium is 1+, magnesium is 2+, versus, for example, aluminium, which is 3+. The more highly charged the ion, the more energy you're going to get released when you make the bond. Okay, let's keep going. Let's compare a couple. Let's compare a couple of lattice enthalpy of formation bits of data and work out what's wrong. Just notice there are some changes that have been made here to correct them. If you've got if you've got a document which hasn't had the errors corrected, there are just a couple of changes here. So just have a quick scan through and just check that what you've got on your slides in front of you is the same as what I've got here, because mine should be mostly correct. Okay, so let's compare sodium chloride to magnesium chloride, for example. Magnesium 2+ has a smaller ionic radius than sodium 1+, because it's doubly charged. That means the electrons are held in closer together. And also magnesium is doubly charged. So it's smaller and doubly charged. Therefore, the enthalpy change of formation value is going to be more negative for magnesium chloride than it is for sodium chloride. And we can see that in our values there. If you compare sodium chloride to magnesium chloride, the only thing that's changed is the sodium versus magnesium. So you've got more doubly charged and a smaller ion. So you're going to get a much greater, that's why we've got a significantly greater exothermic value for enthalpy change of formation there. What about if we compare magnesium chloride to magnesium sulfide? So again, the only thing that's changed here is chloride versus sulfide. So what will that do? How will that make a difference? So sulfide and chloride have roughly the same ionic radius, because we've added in extra electrons, but they haven't, you've added them into the same shell, so you're not going to get much of a difference in size. But that's supposed to say MgCl2, apologies, so please do also double check that one is correct on your sheet. But the enthalpy change of formation of magnesium chloride transfers the most energy because, no, see, that's wrong as well, sorry. Apologies, that's supposed to be MgS. That's why. That's supposed to be MgS. Let me make a note as well, because I've got that wrong on my sheet. So that obviously hasn't been corrected. So that's supposed to be MgS, sorry. So sulfide and chloride have roughly the same ionic radius, but MgS, because you've got Mg2 plus and S2 minus, you've got the transfer of 2 electrons, or the sharing of 2 electrons, let's say, the give and take of 2 electrons. And that means, because they're both doubly charged, you're going to get a greater ionic lattice enthalpy. And that's why if you compare MgCl2 versus MgS, it is a more exothermic process. The formation of the lattice of magnesium sulfide is a more exothermic process. You have more energy released when you make that bond. So just to confirm, in case it's not obvious, the more negative the enthalpy change of lattice enthalpy of formation is, the more negative it is, the larger the amount of energy associated with that bond. So more energy that's going to be given out, or the greater the energy required to break it, if that's what we're doing. Okay, lovely. Let's keep going, because otherwise I'm going to run out of time. So there are lots and lots of definitions that you need to learn when you start looking at Born-Haber cycles, because you're introduced to a huge number more definitions or processes, actually, I could say, that you need to know to do when looking at Born-Haber cycles. One of them is standard enthalpy of atomization. Standard enthalpy of atomization is the enthalpy change when 1 mole of gaseous atoms form from the element in its standard state under standard conditions. This is one of the key errors where that students make when doing Born-Haber cycles, and can be an issue. And so let's just triple check that we're happy. Enthalpy of atomization is the formation of 1 mole of atoms. And the reason we get confused is because often we do it from diatomic molecules, or we use it with diatomic molecules. And so we think it might be 1 mole of the starting reactant. It's not. It's the formation of 1 mole of atoms. So an equation to represent enthalpy of atomization, standard enthalpy of atomization. Actually, let's do that. No, let's do it there. Standard enthalpy of atomization. An equation to represent it might be half a bromine molecule, gaseous, becoming, oh no, sorry, bromine is liquid, let's get that right. Half a bromine molecule, liquid, becoming a bromine atom, gaseous. Single bromine atom, gaseous. That represents enthalpy of atomization, the formation of 1 mole of bromine, not the using of 1 mole of Br2. That's important because if you have a halide within a Born-Haber cycle, you usually have got to have a little red flag that goes up that says, oh, there's number issues here. I've got to think about my ratios and stuff. We'll come to that later if we can. The next thing that is introduced, or one of the things that's introduced, is standard ionization energy. You might have done this in year 12. We bring it back into year 13 because we need to use it during Born-Haber cycles. Ionization energy is the enthalpy change when 1 mole of electrons is removed from 1 mole of gaseous atoms under standard conditions. You can say that it's removed from each atom in 1 mole of gaseous atoms. That's fine, but you don't have to because it is implied. But you have to talk about 1 mole of electrons, and it has to be removed from 1 mole of gaseous atoms. I know there's a lot to think about. I know that each one of these definitions has got something that's slightly different, something that's slightly, that's, you know, might be same in some ways and different in others, and it's really difficult to get them separated in your head. But if you want to excel with Born-Haber cycles, you need to be confident with your definitions. You need to know state symbols, you need to know when they're ions and when they're atoms, and you need to know your amounts, your molar amounts. So for example, here, it's the removal of 1 mole of electrons. So even if we look at, what we're doing, ionization energy. Oops. So because we're removing 1 mole of electrons, and we're moving it from 1 mole of gaseous atoms, so I've got to start with my 1 mole of gaseous atoms, for example, magnesium gaseous. And if I'm removing 1 mole of electrons, I'm going to form Mg plus gaseous plus an electron, not Mg2 plus. So even though we're used to removing 2 electrons from magnesium, first ionization energy is the removal of 1 mole from, in this case, magnesium. It might be that your ionization energy, they've asked you as about the second ionization energy, in which case you would do Mg plus, removing 1 mole. Whatever happens, you're removing 1 mole of electrons, okay? So just make sure if you're doing first ionization energy, it's the removal of the first mole of electrons. If you're doing second ionization energy, it's the removal of the second mole of electrons, etc. And make sure your state symbols are correct. It's from gaseous atoms, so they must be in the gaseous state. What about the next one? Standard electron affinity is the enthalpy change. This is kind of the opposite, basically, of ionization energy. This is the enthalpy change when 1 mole of electrons is added to a mole of gaseous atoms under standard conditions. Again, both gaseous. Again, 1 mole, but this is the addition. So, for example, and again, you can have first electron affinity or second electron affinity. If you've got first electron affinity, it's the addition of the first mole of electrons to a mole of atoms, gaseous atoms. If it's a second electron affinity, it's the addition of the second mole of electrons to a gaseous atom or ion. Could be ion, probably is ion. So, for example, electron affinity is, let's do oxygen, gaseous atom, and I'm adding my first mole of electrons to form a gaseous ion. And in this case, it's only a 1- ion because I've only added my first mole of electrons. I could then write an equation for the second electron affinity, adding the second mole of electrons if I wanted. And then finally, just as a comparison to what we did earlier, standard enthalpy of formation. Sorry, this is where I should have said, this is what we did yesterday, and it is different to lattice enthalpy of formation. This is standard enthalpy of formation, which is the enthalpy change when 1 mole of a substance is formed from its constituent elements in their standard states. Lattice enthalpy of formation is the formation of 1 mole of an ionic solid from gaseous ions. This is the formation of 1 mole of a substance from its constituent elements in their standard states under standard conditions. A subtle difference, but an important one nonetheless. So if we talk about, for example, forming sodium chloride, we absolutely can do enthalpy of formation of sodium chloride, but what's it coming from to go to? What we're doing, enthalpy of formation. If we're doing formation of sodium chloride, it's got to come from its constituent elements in their standard states under standard conditions, which is sodium metal and a solid, half a mole of chlorine molecules in the gaseous state, and it's going to form NaCl solid. So again, there are some similarities, but it is not the same as lattice enthalpy of formation. This is coming, the process when you're coming from elements in their standard states, going to the ionic solid, and lattice enthalpy of formation is coming from gaseous ions to the ionic solid. The enthalpy change for those two processes is different. Okay, hopefully everyone is happy with that. We're going to move swiftly forwards to make sure that we don't run out of time too much. I'm not going to have a go at this exemplar exam question because hopefully it's something that you can do in your own time, or these, because again, we have had a look at them already today. But I am going to move swiftly on to Born-Haber cycles because this is something often we find, and we teach Hess cycles because technically they're simpler than Born-Haber cycles, but it's really interesting. It doesn't happen for everyone, but it's really interesting when teaching these. Lots of students find Born-Haber cycles easier than Hess cycles, even though technically they're more complicated, and that's why they're taught in year 13, whereas Hess cycles are taught in year 12. But I would highly recommend, if you found Hess cycles hard, once you've learnt your Born-Haber cycles, go back and look at simpler Hess cycles and see if you can use the same principles that you've been using in Born-Haber cycles to answer Hess cycles, because it's the same logic. It's talking about Hess's law. It's using Hess's law. But yeah, so Born-Haber cycles are slightly more complicated looking because they involve a lot more processes usually than Hess cycles do. So Hess's law states the enthalpy change for a chemical reaction is independent of the route taken. So again, I mentioned this a bit yesterday, but I'll say again today for those people that weren't here. If I'm trying to get from, for example, home to school, the distance or difference between home and school is the same whether or not I took a bus to get there, whether I went on a nice walk around the hills, whether I went straight there, whether I somehow flew there or took a cable car. The difference, the distance difference between A and B is the same. Doesn't matter how I got there. And it's the same principle with Hess's law. Again, I said yesterday, if you're not comfortable or confident with why that works or why it makes sense, go back to your GCSE maths or physics, actually, your GCSE physics, and look at vectors. See if you can get your head around vectors and vector quantities a bit, because it's a similar thing here. Okay. Energy change has got a positive or a negative, which makes it a vector quantity, or we can use it as a vector quantity. So get your head around vectors and see if that helps you to understand how and why this works. Okay. Also, lattice enthalpies are pretty much impossible to measure directly in a laboratory because there's just too much going on. It's really difficult to make sure you've got the correct amounts of stuff, to keep the conditions in the right way that mean you can measure a lattice enthalpy, because we're starting with gaseous ions and we're going to an ionic solid. So it's really difficult to have conditions that mean that that's possible in one reaction vessel. So instead of measuring it directly, we can use Hess's law to measure it indirectly, using all the other processes that we can measure directly, because they are simpler. So we use Born-Haber cycles. Born-Haber cycles. I believe it's the same Haber as in the Haber process. Born-Haber cycles. You can also use Hess cycles, and they are obviously linked, but this is a slightly more involved diagram. So let's look at an example. Now I'm not going to go through these stepwise steps, because I think Born-Haber cycles and using and creating Born-Haber cycles and Hess cycles is a very personal thing. It's dependent on what you feel most confident with, and I'd always start with what you feel confident with. So I'm not going to go through these individual steps. Please feel free to in your own time in constructing Hess cycles and Born-Haber cycles, but I would highly recommend you start wherever you feel most comfortable. So here we've suggested you start with elements in their standard states. Personally, I actually prefer to start at the bottom with the ionic solid, because that's usually where the ionic solid lives, is at the bottom of the Hess cycle. So it's completely up to you what you would prefer to do. I'm not going to go through these stepwise now. I'm going to try, if we've got time, to skip and just talk through a Born-Haber cycle in an exemplar exam question. So please feel free to have a look through this in your own time. I'm not going to go through this one now, because again, I think it is quite personal. The creation of these is hard. It's very hard, and therefore people need to do it in their own way or take their own time over it. Right, so the process is obviously the same every time, though. So I will go through one. So apologies if your way is different to my way, but yes, do it your way. As an important thing to note, we don't actually often draw them on Born-Haber cycles, but we do have, it is directional. So one of the things that we don't have with Hess's law, arrows have to be pointing in the right direction, of course they do, but with Born-Haber cycles, we have like an up-down vertical axis that's not shown, and that vertical axis is enthalpy is increasing upwards, which means your arrows need to be pointing in the right direction. So negative or exothermic enthalpy changes must point downwards, because that's showing the process gives off energy, so the enthalpy change for that process is needs to go downwards, the enthalpy decreases. And positive or endothermic enthalpies, arrows need to point upwards. So processes that are endothermic, the arrow must point upwards, because as that process happens, you are gaining enthalpy. So just make sure that your arrows are pointing in the right direction. Again, same with Hess cycles. If the arrows are wrong, you're never going to get to a correct answer unless you make a further mistake to get to a correct answer. So make sure your arrows are pointing in the right direction, and starting with the right reactants and ending with the right products. Okay, let's have a quick look at this example, but we are going to skip ahead a little bit to find a different one. So this is an example of a calculation. I will say before we go into it that calcium fluoride doesn't exist. So this, although the maths involved in this question is correct, and I think we did it last year, you're never going to get one on calcium fluoride. So what we're actually going to do is we're going to skip ahead to one of the questions in the mini mock paper and just go through that. Hopefully, it'll only take us about 5 minutes. So I'm going to skip way ahead past, oops, no, let's do it like this. Actually, that's a bit easier. I'm going to skip ahead to, in the mini mock paper, there is this question. I think it's the first one in your mini mock. So you should have this, or should be able to get it in front of you. And we're just going to go through this one instead, because this is the correct salt that is formed, calcium fluoride F2. It also means I can talk to you, or we can remind ourselves about what happens when we've got that little annoying ratio of 2 going on, 1 to 2. Okay, so the question says, complete and label the Born-Haber cycle for the formation of calcium fluoride using the data provided. The first thing I would do, or actually I'll just say, part B then says, using your completed diagram, calculate the lattice enthalpy of formation of calcium fluoride. So the first thing I would always do is, sometimes you actually, let me start again. Sometimes when you're doing Born-Haber cycles, you have to create them yourself. If you do, again, start where you feel confident, where you're confident with the processes that are involved, that species is involved in, and then move around the Born-Haber cycle from there. You may choose to start with species in their standard states. You may choose to start with the ionic solid. Personally, I always start with the ionic solid because it's in the same place every time, which is at the bottom. It's entirely up to you, though. Again, you need to know your definitions. If you don't know your definitions well enough, it's so difficult to construct a Born-Haber cycle. So all you have to do is make sure you know those definitions both perfectly. First ionization energy of calcium. Actually, what I'm going to do is I'm going to label, oops, apparently not. Try that again. Let's go there. Oh, no, I'm on highlighter now. Oops. I'm going to label these as A, B, C, D, E, and F. And then we can place A, B, C, D, E, and F in the right places around the Born-Haber cycle to make sure that we know which each process is, or which process each arrow is representing. So again, you do this your way. If you would prefer to start at the top and work your way down, fine. If you prefer to start at the bottom and work your way around, fine. What I am going to do is I'm going to find the things that I know for sure I know the process of, the ones that I find easiest, which is things like enthalpy change of formation for calcium fluoride, enthalpy change of formation. This is something we learn in year 12, so we should hopefully know it well. This is enthalpy change of formation. This is forming a substance from its elements in their standard states under standard conditions. So enthalpy change of formation of calcium fluoride. This is calcium fluoride. Enthalpy change of formation is from elements in their standard states. So that must be that one. So that one is D. That looks like P. Let's go D. It still looks like a P. D. There we go. What else can I put in? Well, I've been told the lattice enthalpy of calcium fluoride. That one's already in, so lovely. What else do I know? So ionization energies, I feel quite confident with. So A is the first ionization energy of calcium. So first ionization energy, that's calcium losing its first mole of electrons. So starting with a gaseous atom, ending with a gaseous ion. So that must be that process there. So that one is A, that arrow is A. B is the second ionization energy of calcium. Well, there we go. We've got the first one going to the second one, so that makes my life a little bit easier there. So that's B. And then what about electron affinities? Okay, so electron affinity is gaining electron. So the electron affinity of fluorine is fluorine gaining an electron. There we go. Fluorine atom becoming a fluorine ion, fluorine gaining an electron. So that one, that arrow there is C. But what flag has just gone up in my head there. Hopefully yours did as well. It's that this is 2 moles of fluorine. So actually I need C times 2 because I've got to have the electron affinity happen twice or with 2 moles. Electron affinity is only per single mole. So I need 2 lots of C there. What else is happening? What else have I got? I've done D, E, enthalpy change of atomization for calcium. So what's atomization? It's creating 1 mole of gaseous atoms. So calcium, starting as a solid, creating gaseous atoms. It's only 1 mole, so that's fine. So that's E. And then actually, I can just fill the last one in, but let's just double check it anyway. That one's got to be F, enthalpy change of atomization for fluorine. Again, what little red flag has gone off? I can see this is F2 becoming 2F gaseous, and enthalpy change for atomization is the formation of 1 mole of gaseous atoms. Here we're forming 2 moles of gaseous atoms, so we need F twice to make sure that that's correct. Hopefully then you can plug in your numbers if you chose to. The next question asks you to calculate the lattice enthalpy of formation of calcium fluoride. So we'd then go, this is what I'm trying to calculate, this arrow here. I can't go directly there because that's what I'm trying to work out, but I need to start at the beginning of the arrow and I need to end at the end of the arrow, so I can't go directly there. So I've still got to start at the beginning and end at the end, but I've got to go around the other way. So in that case, that involves me going round that way. That means I'm going against the first arrow, so I'd have to minus whatever that arrow is representing. I'm going against that arrow, so I've got to minus whatever that arrow is representing. I'm going against that arrow, I've got to minus whatever that one is representing. Against that one, I've got to minus that one. Against that one, I've got to minus whatever that arrow is representing. And against that, no, sorry, I lied, with that one. With that final arrow, so I can add whatever that final arrow is representing. If I were to plug all of those numbers in, hopefully I would come up with, am I on the right? Oh no, okay, I'm gonna have to skip forwards a little bit because I've started writing this in the wrong section. Never mind. Sorry, I've got my answers here. There we go. So once I've written out, I've done my against, I've minus that one, 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 and plus I've added that one. Once I have plugged all of those numbers into a calculator, oh, sorry, no, once I've written all of those numbers down, I can then resolve any pluses and minuses. So minus a minus makes it a plus a minus is a minus a plus is a minus, plus a plus is a plus, obviously. So once I've resolved all of my pluses and minuses, I can then plug it into a calculator and hopefully come out with the correct answer. I would resolve your pluses and minuses first before you plug it into your calculator, because otherwise you can force your calculator to keep negatives where you don't want them to keep negatives. So resolve it first and then plug it into your calculator. Okay, right, let's go back now. Apologies for that skip ahead, but obviously we don't want to be going through stuff which is not useful. So let's just go back. I'm going to skip back to where we were, or just after where we were, if I can find the right place. Okay, that one. So we're going to go now to assumptions in ionic bonding. Note, this is not in the OCR specification. Whoops. It's not specifically given in the OCR specification. So if you're an OCR student, feel free to listen and digest, but you are unlikely to be expected to recall any of this. You still might be expected to apply knowledge or be given some of this information and then apply it. That's absolutely fine, but you're not expected to recall any of it. So, assumptions in ionic bonding, there's only a couple. Our assumptions are that ions are in contact with each other, so there's no gaps between ionic bonds. Ions are perfectly spherical. Of course, they're not, because atoms and ions aren't solid balls, but this is an assumption we need in order to discuss ionic bonding. And the charge of each ion is evenly distributed in space. Again, that's not the case because electrons move around all the time. The nucleus is the positive center, so the charge across the ion is not going to be evenly distributed, but we have to make that assumption in order to be able to discuss and model ionic bonding. Let's talk or apply this to polarization. Again, this isn't in the specification for OCR, but again, you may be given some information and expected to apply it. So don't completely switch off, but do be aware that you might, this isn't specifically for you. I'm going to take a drink. And I need to speed up a little bit if I can. So polarization is quite hard, I think. Hard to get your head around. Once you understand it, it can be a little bit easier, but it isn't easy. I definitely know that. So the reason we talk about it is because when we are modeling things, when we are coming up with ways of explaining what's happening in the natural world, we have to simplify things. We have to create models in order to be able to explain things, because there's just so much going on. We cannot explain it all at once. One of the models that we have created is ionic bonding versus covalent bonding. Now, these are correct in that they are a really good way to explain what happens between metals and non-metals, or non-metals and non-metals. But they're not perfect. And actually, what happens with a lot of our substances is that there's actually a mixture. There's actually a combination of ionic and covalent bonding happening at the same time. So there's what we call a continuum or a spectrum. We love talking about spectrums because most of the time you can't, put things in two boxes. It is a spectrum, and this is one of them. So ionic solids may not only have ionic bonding, but they also may have covalent bonding. There might be some covalent character to their bonds. What we mean by that is as shown in this diagram. A covalent bond, so the bond, for example, between carbon and oxygen, a covalent bond has electron density between the atoms. There is electron density to be found between the atoms. That's not the best diagram, but we can see that between the atoms, you can find electron density. With an ion, normally, or with ionic bonding, we would consider the positive charge and the negative charge as spheres. My spheres are not brilliant, but as solid spheres. But what actually happens, so the charge, is found in a sphere around the positive ion and in a sphere around the negative ion, and there's nothing between the two. But what actually happens is we find that there is also a little bit of electron density between the two ions, or what we consider to be the ions. And this is the covalent character. This covalent character arises due to polarization. Polarization, what is it? It is a distortion of the electron density, which leads to more electrons being present between the nuclei rather than just around the nuclei. We can get them between the two nuclei. And it means there is an overall, or increases the bond. It means that there is overall a stronger bond. It's stronger because we also have some covalent bond character in there. We also have a little bit of sharing of electrons, as well as the give and take of electrons. So as well as that electrostatic attraction, the two nuclei are also technically sharing electrons. So it makes the bonds stronger. So if there is covalent character, you're going to get a stronger bond between the ions. Polarization, when does it happen? It comes up when small, highly positive cations cause a distortion of the electrons in a large, diffuse, highly negative anion. So what we're looking for are small, charge-dense, positive cations, which are able to steal electron density from big, diffuse negative anions. For example, I love this diagram because I think it's really useful in explaining it, or helping us to see trends, I should say. So, for example, as you go down from +1 to +2 to +3 cations with the same anion, so we've got chloride anions here, which is a nice big diffuse anion. As you go down, the more highly charged and smaller the ion is, so the more charge dense the cation, the better it is at polarizing an anion, and therefore the more covalent character there is. So the more electron sharing is happening between the two nuclei. So for the cation, increasing charge and increasing charge density, because the ion is getting smaller. Increasing charge and increasing charge density. Oh no, actually, let's write it slightly differently, sorry. Let's say increasing charge and decreasing atomic radii. Gives us a higher charge density. Let's do it like that. Higher charge density. The higher charge density means you're going to get, the higher charge density means you get more polarization, greater polarization, which means we get a stronger bond, or a greater bond enthalpy, you could say. I'm going to add in another layer here as well. Greater polarization, which means greater covalent character, which is a stronger bond. Stronger bond. So sorry, there's quite a few steps of explanation there. So let's just go through them again. The bigger the charge, or the greater the charge, and the smaller the cation, the greater the charge density is going to be. Highly charged dense cations even can polarize anions. So the greater the charge density, the more polarization is going to happen. The more polarization you've got, the more covalent character that's therefore showing, and therefore the stronger the bond is. On the flip side, for anions, the key is a little bit easier here. The key here is that the bigger, more diffuse anion you've got, the more easier it is. The easier it is to polarize it. I need to speed up. Increasing anion size, I can't spell size, gives us greater polarizability. As in, it's easier to polarize them. Polarizability. So it's easier to polarize them. So the lower the charge density of the anion, the better they are at being polarized. Excuse me. So increasing polarization means we have greater covalent character. Means the bond is going to be stronger. Character. Let's keep going. We can tell when there is covalent character because we can see the discrepancy between experimental values from Born-Haber cycles and theoretical values from the perfect ionic model, which we get from data books. The difference, or the discrepancy between these two values, tells us the degree of covalent bonding. Because if we have experimentally calculated the value to be stronger than the data book tells us it should be, we know that there is in reality more covalent character present. The theoretical value assumes purely ionic bonds, but polarization actually happens in real life, means we get more covalent character, means the bond will be stronger, and so you'll get a larger or more negative, more exothermic lattice enthalpy. So that will tell us. So this is our model. And in reality, we have a little bit of our covalent character. So electron density between the nuclei, which tends to be stronger. So this is our pure ionic bonding. And this is showing covalent character. Oops, I've gone around the corner. Sorry about that. Okay, I'm not going to be able to do any of these exam questions because we are already running a little bit later than I'd hoped. It's just so much content, so I'm really sorry about that. But again, you will be sent over the answers, so you can have a go at these, and then you can mark yourself when the answers get sent to you at the end. There's just so much content to cover in such little time. So let's just have a quick think about enthalpy of solution as much as we possibly can, and then we can head for lunch. So enthalpies of solution. The first step, this is for everybody again, sorry, this is no longer just, this is everybody, all 3 exam boards. So enthalpy of solution. The first step when you're trying to dissolve an ionic lattice is separating the ions from each other. That's the first step. And it requires energy because you're breaking a bond. And we call that bond breaking the lattice enthalpy of dissociation. It's just the reverse process of formation. So the first step of dissolving a lattice requires energy, and we call that the lattice enthalpy of and I have to make sure I spell it right, dissociation. Lattice enthalpy of dissociation. And like I say, this is just the reverse process of lattice enthalpy of formation. But because we are breaking a bond, it's the same process as formation, but in reverse, we're breaking a bond, so it must be endothermic. We're putting in energy, so the enthalpy change must be positive. We've got to put energy in to break a bond, so it's endothermic. It's also worth knowing this definition off by heart. It's, again, the same as formation, lattice enthalpy of formation, but in the reverse. So standard lattice enthalpy of dissociation, which is positive because we're breaking bonds, is the enthalpy change when 1 mole of an ionic lattice dissociates into its gaseous ions. Again, the molarity comes from the fact that we're breaking up 1 mole of our solid ionic lattice, but we've still got to have our gaseous ions as our products. For example, sodium chloride solid goes to make sodium ions gaseous and chloride ions gaseous. Hopefully nothing major there, but our thingy delta H is going to be positive because it's endothermic. Bonds are broken, we're putting energy in. Energy in to break bonds. Always happens every time. And I'm just going to stick the gaseous ions down there to make sure that we know they're gaseous. Okay, and then what about the next bits? What's happening at the end once we've put things into solution? So once dissociated, once our ions have, the bond between our ions has been broken, that we've separated them, the separate ions can be solvated. That means put into solution. Solvated means that they have been surrounded by water, usually by water. That's true, actually. It doesn't have to be water, but we don't use any other solvents in A-level chemistry. So, we don't talk about the theory behind any other solvents in A-level chemistry. There's no reason why they couldn't apply your knowledge to a new solvent, but water is the main solvent that we use at A-level. So once dissociated, the separate ions can be solvated, usually by water. Water clusters around the ions so that the negative end of the dipole within water surround the positive ions, and the positive end of the dipole on water surrounds the negative ions. So each water molecule, the oxygen is more electronegative, so it's going to have a negative dipole. The hydrogens are going to be delta positive. They've got the positive dipole. And so your chloride ion, which is negative, is going to have an interaction with the positive side, the positive dipole on a water molecule, and vice versa for sodium, our positive ion. So again, the oxygen is delta negative, the hydrogen is delta positive. So you're going to get your interaction between the oxygen, the lone pair on the oxygen, and the sodium ion. I won't draw all of those in because it's going to take forever, but that is a lovely little electrostatic attraction. Electrostatic attraction. This electrostatic attraction is formed when ions are solvated. So if we are forming a bond, that specific process, solvation, is usually, so you're forming a bond. If you make a bond, that you're releasing energy is exothermic. These are more definitions that we need to make sure we have got sorted in our head, and there is a slight difference between them. So let's just confirm we know what the difference is. Standard enthalpy of hydration is the enthalpy change when water molecules surround 1 mole of gaseous ions under standard conditions. So this is the enthalpy of hydration, and it's the hydration of single moles of ions. Sorry, single ions even. So hydration is the hydration of single moles of ions, single ions. Enthalpy change of solution is when we are dissolving, when we're putting a substance into solution. So for example, sodium chloride is being solvated or is going into solution. Sodium chloride is the whole substance. So not a single ion, but a whole substance. That's the difference between the two. Standard enthalpy change of solution is the enthalpy change when 1 mole of solute dissolves completely in sufficient solvent under standard conditions, forming a solution where molecules or ions do not interact with each other. Now you can, instead of saying forming a solution where molecules do not interact with each other, you can say forming let's say, forming an infinitely dilute solution, infinitely dilute solution. And that's another way of saying forming a solution where molecules or ions do not interact with each other. The point is you shouldn't have sodiums and the chlorides interacting with each other. Otherwise, we can't use our model. So this is the idea. This is why we put it in our definition. Enthalpy of hydration follows the same trend as the lattice enthalpy of formation. It will be more negative and therefore give out more energy when we have got smaller ions. We've said that before. Oops, sorry, I didn't mean to do that. Smaller ions and more highly charged ions. So the higher the charge density, the more energy you're going to get when those interactions happen. And the more highly charged the ion is, again, the more energy is going to be released when those bonds are formed. We are running into lunch now, and I'm very aware that I don't want to eat up too much of your lunchtime. So I'm going to do the same thing as I did before. I'm not going to go through this Born-Haber cycle in as much detail as I would like, but please do spend time going through it and double checking you're happy with what each of the processes mean, why the arrow is pointing in that direction, etc. And you can do it in this order, you can do it in whatever order suits you. But I will just say we can use Born-Haber cycles to calculate enthalpy change of solution. They look more complicated, or actually, well, yeah, so some people they look more complicated, some people they look simpler. This same information can also be presented in a Hess cycle. So you can use whichever you would prefer. If you are somebody who finds Born-Haber cycles that little bit easier to get your head around, then use Born-Haber cycles. If you would prefer to use a Hess cycle, use a Hess cycle. The information is the same or using the same principles, it's just the information is presented in a different way. So whichever you would prefer, Born-Haber cycles or Hess cycles, for enthalpy change of solution, you can use both. The only thing I will highlight to you for both is that for enthalpy change of hydration, because it's for single ions, you must make sure you include the hydration of both ions, one and then the other. For enthalpy change of solution, and it's the same for the Hess cycle, sorry. For enthalpy change of hydration, you must make sure you've included both the hydration of both ions. You could do that in one arrow, or if you're the kind of person that likes to use 2 arrows on your Hess cycles, you can do 2 arrows, each arrow representing the different process. Whatever suits you, but just as a highlight, please make sure you remember that. The principle of doing a Hess cycle and a Born-Haber cycle is the same with enthalpy change of solution. Right, I have rushed through that and I'm really sorry. I will just point out you should, in both cases, so here we came up with, that's a rubbish triangle. Enthalpy change of solution as being positive 77 kilojoules per mole. So hopefully if you plug those numbers in, you will get that as an answer. And the same for the Hess cycle. You should also, no matter which method you use, you should come up with the same answer because it's the same process, it's the same principle, it's using the same numbers. It should be the same. Just because you're using a different method to get the answer doesn't mean the process will have a different value. So it should be the same. Feel free to double check those though, and there are a few exemplar exam questions that you can have a go at if you would like as well.